Hello, everybody. Welcome back. Now we have faculty talk for 30 minutes, followed by 5 minutes for Q&A. Our speaker is Shashank Vatedka. Shashank Vatedka received his MSc Engineering and PhD degrees from Department of Electrical Communication Engineering, IISc. He subsequently did his postdocs at Institute of Network Coding, Chinese University of Hong Kong, and Telecom Paris, France, before joining the Department of Electrical Engineering at IIT Hyderabad, where he is currently an assistant professor. He was a recipient of the TCS Research Scholarship during his doctoral studies, the Sheshagiri Kaikini Medal for Best in the Department of ECE at IISc, the runner-up for the Best Paper Award at SPCOM 2020, and the Best Poster Award for the 2021 Stanford Compression Workshop. His research interests are in information theory and coding with applications to security, data compression, and statistical inference. He will give us a talk on data compression with locality. Welcome, Shashank.
Thank you, Satyajit, for the very kind introduction. And I'd like to thank Professor Adrish and the organizing committee of JTG Summer School for kindly inviting me to give this talk. It's always a pleasure to give a talk at this summer school. So this talk will be about data compression. So it's a new take on an old problem in some sense. So this is joint work with Aslan Chamkertin, who's a faculty at Telecom Paris, and with Venkat Chandar, who's with D. Shaw in New York. So to start with, let's look at this block diagram, which all of us would have seen in a first course in information theory, the basic source coding problem, where you have a file which is maybe of n bytes long, and you want to compress it to maybe k bytes, where k is much less than n. And the goal is to design this compression decompression algorithm so that you can eventually reconstruct the original file from the compressed one, right? And traditional compression, or traditional lossless compression, I should say, has been designed and studied in the mind of with the idea of archival purposes, right? So the goal is, for example, if you think of a compression scheme like zip or basically Lempel-Ziv or Huffman codes or variants, the main objective here, or the main goal of using such compression algorithms, is that you have a large file, you compress it, and then you store it, and later on when you want to extract, the file once again, you just decompress it, right? But today our requirements are changing. So today we don't just store files and then view the whole thing later on. We also interact a lot with the data, right? So for example, think about a problem where you want to, maybe say Google Drive Google wants to compress your entire Google Drive folder, right? So that's maybe around 20 gigabytes in size. So if I compress all of my Google Drive folder, all of the 20 gigabytes, then maybe I can bring it down to maybe 10 gigabytes or so, right? So this is very space efficient. But unfortunately, if I want to, say, extract one file, if I want to, say, read a particular Word document in my Google Drive folder, then the only way I can extract this is by decompressing that entire Google Drive folder and then reading it, right? Similarly, if I want to modify it, then I have to basically decompress the entire Google Drive folder and then recompress it, right? So if you think of this Google Drive example, you interact a lot with the files in your Google Drive folder, but at any point in time, you're only accessing a very small number of bytes of data, right? So your Google Drive is maybe 20 gigabytes of size, but then at any point in time, you're only maybe reading and writing a few megabytes at most, right? So is there a way to sort of also to get good compression on the cloud, but at the same time be able to efficiently access the files along at the same while at the same time obtaining the same amount of compression as, say, zip. Right. So let me put it a little more formally, and let's look at some of the motivations here as well. Right. So a lot of our data today is stored on the cloud. Right. And if you want to make efficient use of the storage space, we want to compress it. Right. And but it's not just storage that we have to keep in mind. We also want to keep in mind the amount of accesses that are made. So close to 70% of internet traffic is basically due to communication between data centers and with clients with data centers. Right. So we want to be able to efficiently store large volumes of data, but at the same time in a way where we can manipulate it frequently and as efficiently as possible. Right. So let's look at what our goal is. Right. So suppose I have a very large file. This could be a large database, or it could be a large connection of, say, genomic sequences, and or even your Google Drive folder. Right. So I compress this large file or large folder and store it on the cloud. Okay. Now, my goal is to somehow design a compression algorithm so that if I want to access a small portion of the raw file, then I should be able to do so without decompressing the entire file. So suppose if I had used zip to compress my large file, then even if I wanted to obtain maybe one word of my large file, the only way I can do this is by decompressing the entire file. And I don't want to do that because that is very inefficient. So I don't want to decompress 20 gigabytes in order to extract maybe just 1 megabyte or just a 1 megabyte Word document. Right? So I want to design a compression algorithm that lets me do the following. If I give a particular location, then I should be able to extract the word in that particular location, that word in the raw file, by accessing a very small number of compressed bits which are stored on the cloud. Okay, so the compressed file is stored on the cloud, and I should be able to decompress the second word in this example by accessing a very small number of compressed bits. Okay, so this is what I call local decodability. So I should be able to locally decompress the file. Right? At the same time, if I want to say update, say, one Word document in my Google Drive folder, then I should be able to do so without sort of decompressing and recompressing everything, that all of that 20 gigabytes. Okay, so if I want to say replace one word of my document, then I should be able to do so by modifying a very small number of compressed bits. Okay, so again, to give you the example of say zip, if I wanted to even replace one word in my document, then the only way I could do this was by first decompressing the entire file, making that change, and then recompressing that entire file. Right? And this is something which I really want to avoid. So we want to design a compression algorithm which minimizes the storage space, but at the same time, I also want to minimize the number of compressed bits that I need to access or modify in order to, say, recover. So I want to minimize the number of compressed bits that need to be accessed to recover a single message symbol, and the number of compressed bits that need to be updated or modified in order to update a single message symbol. Okay. So so let's start with some basic formalism. So let's look at fixed length compression, something that we're all familiar with. So for now, I'll just assume that my message or the raw file is an IID sequence. Okay, and I compress this to a rate R code word. Okay, so the length of the code word the code word is basically a sequence of n bits, so which has length n. Which has length nr. All right, so and by decompressing this, I get an estimate of the message xn hat. So in fixed length compression, my r is fixed, but what I want to guarantee is that with very high probability, xn hat is equal to the original message xn. Okay, and we know from basic source coding, so Shannon showed that you can achieve a rate of h of x times 1 plus epsilon, while at the same time having a probability of error. So the probability that xn is not equal to the reconstructed xn hat can decrease exponentially in n. Okay, and this is, again, this is not without any local compression decompression constraints. This is just standard source coding. Okay, now I want this additional requirement, which I call local decodability, wherein from the code word I want to be able to not just be able to extract the entire raw file, but also be able to decode locally. So the local decoder is going to be an algorithm which, given a particular location, suppose I want to extract only xi, then I should be able to do so by probing a very small number of compressed bits. And so by only accessing a small number of compressed bits, I want to be able to reconstruct xi, okay, and get xi hat. Okay, and I define the local decodability as the maximum number of compressed bits that I need to read in order to recover only xi hat. Okay, and this is maximized over all possible I and all possible message sequences xn. Okay, so this is one requirement. I want to be able to locally decompress by accessing a small number of compressed bits. Okay, and there are different notions of local decodability that one can study. So one is you maximize over all possible input sequences, all possible raw files. And the other is you can also look at the number of compressed bits that you need to probe on average, where this average is taken over all possible all possible input files or all possible input sequences. Okay, so similarly, now we don't just want to be able to locally decompress efficiently. We also want to be able to update the file or update small parts of the file. Right? So suppose I have a message x1 through xn. So this is the original message, and let us say that I want to replace only the ith symbol of the message. So this could be the ith byte of my file, for example. Right? So I replace the ith symbol xi with some xi tilde. Okay, so and if the compressed version of the original sequence was this, then I should be able to modify only a small number of bits and get the code word corresponding to this new message. Right? So basically, making small changes to the message should correspond to making small number of changes in the code word. So in this particular example, I can replace the ith message symbol by replacing or basically by modifying only 5 bits of the code word. Okay. So my update algorithm, in fact, I'll require something even stronger. So my update algorithm is going to take only 3 inputs. One is the location which needs to be updated, the original symbol in that particular location, and the new symbol which it needs to be updated with. So in location I want to replace xi with xi tilde. The update algorithm has no information about the rest of the message or the rest of the old code word, and it has to, if it wants to know more, it has to probe. Okay, so the update algorithm is allowed to probe a small number of bits of the old code word to get whatever additional information it requires, and then make a small number of changes to get the new code word corresponding to the new message. Okay, and my update efficiency is going to be the total number of bits that I need to read and write in order to affect this. So in particular, I emphasize that the algorithm should be oblivious to xn or the code word CNR. The only inputs it can take a priori is I, xi, and xi tilde. If it wants to know anything more, it has to probe the old code word and make modifications to it to get the new code word. Okay, and the worst case update efficiency is the maximum or all possible I, maximum or all possible choices of the old message and the new message of the maximum of the total number of bits that need to be read and written in order to make this update. Similarly, you can define an average update efficiency, which is the expected number of bits that need to be read and written in order to replace a single message. So to summarize my requirements, I want to design a compression algorithm whose rate, a fixed length compression algorithm, whose rate is still close to the entropy as we had in Shannon's setting, as well as I want to minimize the number of compressed bits that need to be probed in order to recover a single message bit or a single message symbol, and the number of compressed bits that need to be read and written in order to update a single message. Okay, and we want to design a good algorithm, so we should be able to encode and decode using a small number of options. So I'll maybe pause for a couple of seconds to see if there are any questions.
How many number of bits, like minimum bits, you need to probe to recover your signal?
Sorry. So that is what I want to minimize, right? So for example,
is there any lower bound on that? Like any known bound that you at least need this much bits?
In fact, no. So I'll get to that in maybe a couple of slides.
Okay.
But a priori, no, we don't have any idea. So for example, if I used, say, lempel zip, okay, so in the worst case, the number of bits that I need to probe is equal to NR, right? And the number of bits that I need to probe and modify, that is also NR, right? So all of these are schemes. So traditional compression algorithms are schemes wherein you need to probe order n number of bits in order to either locally decode, to extract even a single message symbol, or to update a single message.
I also have a similar question. So
Sure.
it seems that there is some trade-off between rate and number of bits you need to probe. So is there any result on that trade-off?
So I'll get to that in a couple of slides.
Yeah,
I just want to make sure that the problem setting is fully clear at the moment. Okay, so maybe I'll proceed and then we can go. Okay, so even before we sort of get to optimal algorithms, let's see what an obvious solution could be. So if you pose this problem to a practitioner, what would you think of? So the most obvious thing to do is that you have this large file. The best thing, if you want to be able to do local compression and decompression, then the best thing to do would be to split your large file into smaller chunks and then compress each chunk separately. So therefore, if I wanted to, say, extract a symbol maybe at this particular location, then all I need to do is decompress this particular chunk, right? And if I want to update that particular symbol over there, then all I need to do is recompress this particular chunk. Nothing more is required. Like I can do it independently of all other chunks. Now, if I use a fixed length compression algorithm to compress each chunk, then we know that if you want the overall probability of error to be vanishing in n, then the probability of the overall probability of error is basically number of chunks times the probability of error of decoding each chunk, and the probability of error of decoding a particular chunk is exponentially falling in the size of the chunk. So if you think about it a little, if you want the overall probability of block error to be vanishing in n, then the chunk size should be at least as large as order log n. You can't make it any smaller than logarithmic in n. Okay, so this is an obvious solution, basically chunking, and this is used very widely in practice. So if you look at most, say, cloud storage providers, or even people who work in financial companies, when they have large data sets, the best thing that they do is you split the large file into small chunks and then compress. And this gives you this local decodability. Okay, but the question is, can we do better than this? Can we get so of course it's better than, say, plain vanilla lempel zip, where where the local decodability and update efficiency is order n. Now we have come down to order log n. So this problem of compression with local decodability and update efficiency has been studied to some extent in prior work, separately in the computer science and the information theory literature. So in the computer science literature, the model is slightly different. The message is not random, but you look for the worst case message. And the sort of model that I've looked at. So the goal now is to minimize the number of bits that need to be probed or the number of bits that need to be modified in order to update or read a particular symbol. And in this case, it is not even known in the computer science literature if you can get close to entropy, even with sub-logarithmic locality. There are other models known, wherein the so-called self-probe or word RAM models, which I don't want to elaborate on. But here you know that you can do it using a constant number of word probes, but still you can't do any better than order log n bit probe. So you still need to probe order log n bits in order to get in order to achieve a rate close to the empirical entropy of the source or empirical entropy rate of the source. Okay, in the information theory literature, so local decodability and update efficiency has been studied separately by a number of works, starting from Mossel and Montanari in 2008 to more recently Paranjali and Kotran. And there are other versions known here as well, and I won't elaborate on them in this particular talk, but this is basically the state of the art today. So it is known that if you want both simultaneously, you want to get good local decodability and good update efficiency, then if you want if you want to achieve a rate close to the entropy, so maybe h of x plus epsilon, then you obtain the following local decodability update efficiency pair. So you can make the local decodability a constant, the worst case local decodability a constant, but the update efficiency is order log n. Or you can also get a local decodability of order log n and update efficiency, which is a constant independent of n. Right? And constant is basically the best that we can possibly hope for. Right? And we have separate results where so our contributions were the following. So we gave separate algorithms where the worst case local decodability and the worst case update efficiency is much better than order log of log n, but this is worst case local decodability and update efficiency. Now, if you relax the worst case locality constraints to average, so if you only want to minimize the expected number of bits that need to be read or written in order to make a single change to a symbol or locally decode a particular symbol, then you can bring it down to constants. So these constants, of course, depend on epsilon, that is the gap from entropy, but otherwise is independent of the size of the message, is independent of n. Okay, and for both of these, we have explicit polynomial time algorithms. So both the compression, both local decompression and global decompression can be done in just quadratic time. Okay, so since we're a bit short of time, I'll just give a very high-level overview of the idea involved in designing such an algorithm. So we know that if we use, say plain chunking, if I split the file into small chunks and then compress each chunk, then I need to have the chunk size to be at least logarithmic in n. If I make it any smaller, then the probability of error, the probability of block error, is no longer vanishing in n. And in fact, if I bring it down to a constant, if I split my n-sized file into constant-sized chunks, and I try to compress each chunk separately, then with very, very high probability, a constant fraction of them are going to be in error. Okay, but what we do is that, so this was a scheme given by Mazumdar and Tatwawadi and others. So you can do the following. So in addition to the reconstruction vector, in which there are going to, a constant fraction of these chunks are going to be in error, you can also consider the error vector. So I can write my original message sequence as the reconstruction vector, the reconstructed vector from this chunk-wise compression plus an error vector. But we know that only a small fraction of these chunks are going to be in error. So this error vector is going to be sparse. So most of these vector is going to be all zeros, and it's going to have maybe some n times delta number of non-zero elements. Okay, so what we do is, in addition to storing these compressed symbols, compressed chunks, I also store this error vector using a separate data structure. And it turns out that this problem has been studied, and you can construct a locally decodable data structure for sparse sequences. So this only guarantees good local decodability. It doesn't guarantee good update efficiency. So basically what you store are the compressed versions of each chunk and this data structure, which is locally decodable for sparse sequences. And that was the basic idea used by Mazumdar and others. And basically how you get to order log n local decodability and update efficiency is basically by modifying this data structure. Instead of using this particular data structure for sparse sequences, we designed a separate data structure for sparse vectors, for which you can both locally decode and update using just order log n bit probes. Okay, so the basic idea is still the following. You just split your entire file into chunks of size order log n, and then you do either lossy compression or lossless compression of each chunk, and then you can write the message sequence as a reconstructed sequence plus an error vector. So if I want to, say, locally decode a particular symbol, if I want to locally decode some symbol over here, then I can do that by first reading the compressed version, right? So I can read order log n bits. And if this is not sufficient, then I can locally decode using and I also read the error, the data structure storing the error vector, and I can reconstruct the symbol that I'm interested in. All right, so that is the basic idea that is used. So in some sense, my problem of locally decoding and locally updating a general sequence can be reduced to a problem of locally decoding and locally updating sparse sequences, and we can construct algorithms to locally decode and update. So efficient, algorithms where you can compress these sparse sequences to a rate just n delta to just delta, which is very, very small compared to h of x, and then be able to locally decode and update. All right. So the key component is basically a dynamic data structure for sparse sequences, which takes very little space, but at the same time is very efficiently locally decodable and updatable. I have only 2 minutes left, so I won't go into the details of this. But we also have a lower bound. But the lower bound comes under certain assumptions. So we've shown that under some strong assumptions, any fixed length compression algorithm which achieves a non-trivial rate for binary sequences must necessarily satisfy this inequality, which means that the minimum of the worst case local decodability and update efficiency should grow at least as fast as log n. And the basic idea behind this is to look at a particular the so-called encoding and the decoding graphs and try to get bounds on the degrees of these graphs. So if you can construct these graphs and the degrees of these graphs correspond to local decodability and update efficiency of your particular algorithm, and under certain constraints on these graphs, you can show that if you want a vanishingly small probability of error, then it had better be the case that you probe at least order log n bits. Okay, so basically there are these very nice problems on compression where you want to be able to efficiently locally decode and update and perhaps search. And frankly speaking, not much is known about these problems. A lot of problems are still open. And we've designed compression algorithms. We only scratched the surface. We've designed compression algorithms which achieve constant average local decodability and update efficiency. But in the worst, so if you want to minimize the worst case local decodability and update efficiency, then there are still quite a lot of open problems. We can achieve order log n locality, but the lower bound is only under certain restrictions. So, and we don't know what is the best that we can achieve using variable length compression. And how do you design practical compressors which work for even small n? That's a problem that is still very much open. So with this, I'll conclude. I'd be happy to take questions and maybe tell more about things. Yeah, I see that there is one question. Can this framework be extended to a joint source channel coding setting? Well, from what I know, as far as I know, no one has looked at this problem till date. So channel coding with locality has been studied to some extent, but I guess one issue is that it again depends on how you set up the problem, perhaps. But I'm not sure if the joint source channel coding setting will have a particular application. Since you want locality, the plain source coding setting is very much relevant because you have a large data center and where you store and you want to locally be able to decompress. So are you talking about joint source channel coding in the setting of I guess distributed storage or something of that sort?
There is another question.
Sure. So it's a general regular LDPC code. You can show that LDPC codes with right. So it's just a random regular LDPC code, and all you basically so the main idea there is that if you want to update so it's just syndrome encoding of LDPC codes. And if you want to update a single message bit, then all you need to do is XOR that particular row of the parity check matrix, which is parsed. So that automatically gives you a small update efficiency. But of course, the local decodability is still fairly large. You can't make it any smaller than order log n. Okay, so any preliminary thoughts on variable length compression? So the key limitation is really in updating. So for example, if I try to use any scheme which involves, so the problem with using variable length compression is that the ideas that we have work for local decodability. It works very well. But then when you do a large number of updates, it's possible that the overall sequence, which maybe originally was typical, after a certain number of updates, locally it could still be typical, but overall it could be atypical. And at that point, you don't know whether the sequence is atypical unless you probe the entire. So that is still a challenge because a small number of local changes, a large number of small local changes can make large global changes. And at some point, you will need to sort of rewrite the entire code word sequence, and that problem is still kind of.
Okay, thanks, Shashank. I thank both the speakers on behalf of the audience, and I'm sure there will be many more questions. So if any, I have, so just contact the speakers. And both are very interesting talks. First on the structured index coding problem and this compression with locality constraint. Thank you. And now I'll hand over to Professor Adrish Banerjee.
Yeah, thank you, Satyajit and Shashank. So now we will take a not really a break. We'll just go to the launch and come back, and then we'll view a video about what is 5G from Qualcomm. Give me a minute. We'll just go to the launch for a minute and then come back.